Hello everyone. Today I'm here to introduce our project for SC1015 that is based on image classification. We will be discussing the problem, the EDA, the models used, and finally the insights gained from this. The problem we identified is that traditional image classification algorithms can struggle to accurately classify complex images due to the high-dimensional nature of the data. Our aim is to explore ways to overcome this challenge through classifying the SC1015 dataset and analyzing the influence of each image on the model's classification performance. To start, we analyze the SC1015 dataset, which is a popular benchmark dataset for image classification tasks. It is imported from the PyTorch datasets library and consists of 60,000 32 by 32 color images divided into 10 classes with 6,000 images per class. Some examples of classes as seen above are airplane, bird, and horse. We prepared the dataset for the CNN by normalizing it using PyTorch functions based on the mean and standard deviation of the raw data. This is an important step in pre-processing the data to ensure that the images are on a similar scale and to avoid any bias towards particular features of the data. After normalizing, our mean leans towards 0 and our standard deviation leans towards 1. Next, we learn to analyze the color distribution of the normalized SC1015 dataset to gain insights into the dominant colors in the images and identify any potential biases or patterns in the data. We plot the data on matplotlib subplot to plot multiple histograms. As the data is generally centered around 0, the colors are well balanced and normalized. However, blue leans towards an intensity of -1, meaning that the images may be biased towards lighter images, possibly due to the image lighting. Following the analysis of color distribution, we looked at the pixel intensity of the dataset to identify any dominance of light intensity in the images. We plot the data on a histogram. As the data is generally centered from -1 to 0, which is the mean, it means that normalization managed to reduce the effect of a variation of brightness in the images. Finally, we conducted a principal component analysis of the SC1015 dataset. PCA is a powerful tool from scikit-learn that we learn to use that helps us reduce the dimensionality of the data by summarizing the relationships between different features and visualizes the patterns and clusters in the data. As the data belongs in clusters, it means that normalization has made it easier for CNN to distinguish between them. In conclusion, our exploratory data analysis of the SC1015 dataset showed us that normalization of the images has helped us better prepare our images for neural network by reducing the biases in the images. Now we move on to data modeling, where we classify images from the SC1015 dataset. For this, we use the convolutional neural network, or CNN for short. Convolutional neural networks are a type of deep learning neural network that are commonly used for image classification, object detection, and other computer vision tasks. The key feature of a CNN is its ability to automatically learn hierarchical representations of image data through the use of convolutional layers. A CNN typically consists of several layers, which includes the convolutional layer, pooling layer, and a fully connected layer. The convolutional layers apply a set of learned filters to the input image, producing a set of feature maps that capture local patterns and structures in the image. The pooling layers downsample the feature maps by taking the maximum or average value within a local window, reducing the spatial resolution of the feature maps and increasing their robustness to small variations in the input. Finally, the fully connected layers take the flattened feature maps and perform a classification task by mapping them to a set of output classes. Here is the code for our CNN. The first convolutional layer takes an input tensor with 3 channels corresponding to the RGB color channels of an image and applies 6 filters of size 5 by 5. The output of this filter is then passed through a max pooling layer that downsamples the output by a factor of 2 in both the horizontal and vertical dimensions. The second convolutional layer takes the downsampled output of the first layer, now with 6 channels, and applies 16 filters of size 5 by 5. Again, This output is passed through a max pooling layer. Next, we have 3 fully connected layers. The first takes the flattened output of the second convolutional layer and maps it to a 120-dimensional feature space. The second layer maps this down to an 84-dimensional feature space, and the final layer maps it to a 10-dimensional output for each of the 10 different classes. The forward method is a required method for the PyTorch module, and it defines how the network should perform a forward pass from the input to compute the output. The input tensor X is constantly transformed while moving through the layers. We did training over 10 epochs, and this is what we found. During training, the CNN updates its parameters, which is its weights and biases, using an optimization algorithm to minimize the loss function. This loss function measures how well the network is able to predict the correct output for a given input. From the graph, we can see that as the number of epochs increases, the loss function for the training set decreases, while the loss function for the validation set decreases as well, but at a lower rate. If the loss function for the validation set increases instead, this may suggest overfitting, and we should stop training in that case. As for the accuracy of the model, we can see that both the train accuracy and the validation accuracy increases as the number of epochs increases. Here is the confusion matrix. It shows the number of true positives, false positives, true negatives, and false negatives for each class in the dataset. For the CIFAR10 dataset, we have a 10 by 10 table for each of the 10 different classes. From our results, we can observe an average accuracy of about 60%, with cars and ships having a higher average accuracy, while cats and birds have a lower average accuracy. The table allows us to see which classes are easier or harder to predict, and allows us to tweak our model as such. Moving on to influence and insight, this section will delve deeper into the planes and cars classes within the CIFAR10 dataset. The images with a harmful influence primarily resemble planes or cars, whereas those with a helpful influence do not strongly resemble planes or cars. Focusing on the planes class, our observations suggest that the model may struggle to differentiate between specific planes and other classes, leading to misclassifications. One possible reason may be visually similar features between planes and other classes, such as shapes, colors, or background elements. For example, a plane's wing might resemble a ship's fins, or a car's streamlined shape could resemble a plane's fuselage. Additionally, the model may not have been exposed to a sufficiently diverse set of training examples, limiting its ability to generalize well across various planes and other classes. On the other hand, the helpful images that do not resemble planes may aid the model in identifying the distinguishing features of other classes, thereby improving classification accuracy. These images could contrast the defining characteristics of the plane class and other classes, enabling the model to focus on features that is unique to each class. For example, an image of a bird or a kite in the sky might help the model better recognize the unique features of planes, such as their wings, engines, or landing gears. To conclude, these findings underscore the significance of examining individual image contributions to gain a deeper understanding of the model's behavior and identify potential areas for improvement. By addressing these issues, such as incorporating more diverse and distinct training examples, or refining the model's feature extraction capabilities, we can further enhance the model's performance and achieve a more robust image classification system. Our analysis using influence functions has yielded invaluable insights into the behavior of the CIFAR10 dataset and its impact on the model's performance. We hope these findings serve as insights to developing even more advanced image classification systems. Thank you for your attention.